Assalamualaikum warahmatullahi wabarakatuh. Today, me and my friends want to tell us about liquid drop model. So, here the introduction. The motive is to identify the masses of nuclei and their binding strength. It is called the liquid drop model since nuclei are thought to behave similarly, at least in first order, to a liquid. When the walls force pull the molecule in a liquid together, which is only between near neighbors. We have already seen that the nuclear force is a short-range force which only seems to be acting between neighboring nucleons. Two nuclei with odd number in which the number of protons is equal to the number of neutrons in the other nucleus and vice versa.
What is binding energy? Binding energy is the amount of energy required to separate a particle from a system of particles or to dispose of the particle of the system. The mass of a nuclide is given by Zmp plus A minus of Zmn minus Baz divided by C power of 2, where Mp is the mass of the free proton and Mn is the number of free neutron. B A multiple of Z is the binding energy of the nucleus with mass number A and atom number Z. The factor B A multiplied by Z divided by C power of 2 is known as the fact of the nucleus. Binding energies per nucleon increase sharply as A increase, peaking at iron and then decrease slowly for the more massive nuclei. So the next slide, you can see that what I'm talking just now. The graph of a nuclei binding energy per nucleon.
Let's move on to our first terms, the volume terms. Each nucleon has a binding energy which binds it to the nucleus. Therefore, we get a term proportional to volume. This terms due to the short-range attraction between nucleons. And from this term, we can get the equation where binding energy equal to volume term constant times the number of a nucleus. The second term is a surface term. The surface term states that the nucleon at the surface of the liquid drop only interact with other nucleons inside the nucleus, so that the binding energy is reduced. The surface term states that the binding energy will be reduced by the amount proportional number of the nucleons on the surface. And from this term, we can get the equation where binding energy equal to negative surface term constant times A power of 2 over 3. The term is the Coulomb term. The Coulomb repulsion between the protons in the nucleus also reduces the binding energy. The Coulomb potential energy will be proportional to the square of the nuclear charge and inversely proportional to the nuclear radius. There are other terms in the liquid drop model, the asymmetry terms. Imagine that the neutrons and protons are in a potential well or the nucleus. We will assume that the well has almost equal space and energy levels. Let the spacing be the delta E. Neutrons and protons are feminines, so the Pauli exclusion principle allows only 2p and 2n in each level. For a nucleus with a given A, the lowest energy will be when n equal to z. If we change a neutron to a proton, we will increase the energy by 1 delta E from z minus n equal to 0 case. If we change other neutrons to a proton, we increase the energy by delta E from a total change of 2 delta E from z minus n to 0 case. The adding neutrons to a proton, we increase the energy by 3 delta E for a total change of 5 delta E from Z minus N equal to 0 cases.
So right now I'm going to present about pairing terms. It is founded that 2 protons or 2 neutrons bind more strongly than 1 neutron, 1 proton and 1 neutron. To experimentally observe, the phenomenon is added a term to the binding energy if the number of protons and the number of neutrons are both even. The term is then subtracted if they are both odd, and the term is remain unchanged if one of them is odd and the other is even. Born and Mortensen showed this term as inversely proportional to the square root of atomic mass, which is the equation below. Most nuclei with an A20 or more, this formula, which is the complete formula above, is very well suited to determine the binding energy, which is has a better percentage, which is better than 0.5%. Since there are different isotopes of element for different type of elements, they have different atomic mass numbers. Therefore, each isotope have a different binding energy respectively, and some isotopes are more stable than each other. Lighter nuclei, the stable isotopes, have roughly the same number of neutrons as the protons, but when above A, which is above more roughly around 20, the number of neutrons increase up to approximately half of the number of the protons to be stable for a heavy nuclei. The reason for this arises because of the column term. Protons tends to bind less tightly than neutrons because they must overcome the column repulsive between them. Therefore, energetically favorable to have more neutrons than protons. Up to a certain limit, this column effect, will beat the asymmetry effect, which favors equal numbers of protons and neutrons.